All right. So in this lecture, we're going to continue our discussion regarding the evaluation on multiple projects. And we're going to introduce another concept which is called internal rate of return. Internal rate of return, this method also help us to find out if we should accept a project or reject it, right? So, but internal rate of return, instead like MARR, we already know at the beginning, right? We know MARR. That's it's interesting. MARR is actually sounds more internal because that's something you are interested in. That's something attractive to you. If you want to invest your money into a stock market or into your friend's startup company, you already know that I want to make 20% of profit. Otherwise, I'm not going to do that. That's your uh, minimal attractive rate of return. Internal rate of return, although it's called internal, it's actually about more objectively understand the project. It's more objectively understand the project. At the beginning, we actually don't really know what is internal rate of return. That's actually something we need to find out. That is actually something we need to find out. How do we find out internal rate of return is that we look at all the revenues, so basically all the inflows, as well all the costs, so the outflows, cash outflows, and then we put them all together. We guess what will be the IRR, the internal rate of return, to bring the present value to zero. Let me say this again. At the beginning, we don't know the IRR. Instead, not like MAR, which is something we know we want. IRR is objective to a project we don't know. We don't have that yet. What we have is revenue, we have cost, we also have the number of years. All those information, we try to find out the IRR that can make the present value equal to zero. That is called the internal rate of return. A lot of times, it's also called investor's method, discounted cash flow method, or profitability index. Profitability index. In fact, IRR most widely used method for engineering economic analysis. For this is that the IRR is used more widely than MARR because it sounds easy to say that okay, I want to have some MARR. Usually it's not, right? Think about it. How do you know if you want to make a 20% profit or 30% profit? It's always changed, always based on situation, environment, right? And if a 20% of return can give you can help you earn $2 million compared to a 30% of MARR that can give you $200, well, you're going to think about which one I want to do, right? Yeah, you invest more, but you also get more, right? That's why MARR a lot of time is hard to find. What we do want to find is MARR, and based on that, we can decide if that's some project we do want to do or not. So it can be described in a graph and mathematical equations, right? So the graph, like we said, we already know the revenue, which are RKs on top, all the white arrows. And we know the expenditure, so all the E's on the bottom, the orange arrows here, right? We know all this, and we know how many years. Look, 0 to n. We already know the n. We see the cash flow. We know what is n. The only thing we don't know is IRR. We don't know the internal rate of return. A lot of times also called I prime. That's something we need to find out. And once we find out IRR, that help us to bring our present worth to 0, and it's exactly 0. It's exactly 0, right? Once present worth equals to 0, of course we broke even, and then that's why IRR is also known as a break-even rate. Break-even rate, right? And mathematically, we can write it like this. We want present worth equal to 0, right? That means once we use I prime to convert all the future revenue to present value, that should be equal to use the same I prime to convert all the future values to its present value. So the expenditure's present value is equal to the revenue's present value. Then one minus the other, we got 0. One minus the other, we got 0, right? And so based on this, we find out I prime. Once we find out I prime, we theoretically we calculate, right? We have I prime, I have my I prime, I have my MARR. If I prime is higher than the MARR, okay, alternative is acceptable. And back on what we said before, right? If I find out that one project or one startup I want to investigate give me 5% of interest, and my MARR is 4%, that is the amount to pay down my mortgage, I'm going to go for the startup, right? So it's the same thing, right? If your friends can help you with recommended you a stock you can investigate, and then the I prime's 20%, which is higher than if you investigate into the maybe a index fund, which is maybe give you 15% of return, you're going to say, okay, that's good, I'm going to do it, right? I'm going to investigate into this stock. So the concept is relatively simple and straightforward. The challenge is, if you recall, it's actually pretty hard to find I prime with all the other information. Remember when we talk about how to, based on present value, find a future value, based on annuity, find a present value, and all the different things, find n. Even finding n, it's pretty easy. However, to find I to bring PW equal to 0, that's actually hard. That's actually hard. It's a continuous process, right? Once you have a really low IRR, the internal return rate of return, then the present value is usually high. When you start to increase I prime, it starts to decrease. The present worth starts to decrease, until at one point it's equal to 0. That's the I prime, the IRR you want to find. That's the I prime IRR you want to find. In fact, all the others, you cannot call them IRR, right? Only at this point, this is IRR. Then once the interest rates start to increase again, the present value starts to become negative and keep decreasing. This is hard because this is I is inside a bunch of equations. A lot of times it's really hard to calculate. So if you only have a pencil and a paper, or you only have a really basic calculator, what you can do is do trial and error solution. So basically, okay, you look at this cash flow, you think maybe 15% will bring it back to 0. Then you do the calculation, you find out, okay, with 15%, I'm actually here. So, okay, now the IRR I estimated is too high. So then I go back to maybe 10% is here. Then you find out, okay, the present value is actually positive. Now, well, so 10% is here, 15% is here. That means I prime is between 10 and 15%. Now you want to maybe bring it to 12% and calculate again. Maybe it's up here. Then you do 13% here. Then you do 12.5 here. Then you do 12.7 is here. So finally you start getting narrower and narrower, and you find out the IRR. That's how you find the IRR, right? This is given that if you only have a pencil and a paper or a basic calculator. If you do have your computer and Excel, it's going to be much easier, right? In Excel, you can use IRR function or the rate function to calculate the I prime, So we're going to look at an example, and hopefully that will help you understand a little better. The example here is the one we used before, right? A piece of new equipment has been proposed by engineers to improve the productivity of a construction company. The investment cost is $25,000, and the salvage value is $5,000 at the end of 5 years. Improved productivity will result in $8,000 a year, and the MARR equals to 20%. Is it a sound proposal? We already did this many times before, right? We know it is sound. We know it is sound because based on the MARR, the present value, the future value, the annuity, they're all positive. Right? So we should come to the same conclusion if we use I prime. Of course, all things I have showed here, but this table basically shows, how we use the trial and error solution to find out roughly where is IRR. You see, why set I equals to 0.000%, right? Then all this money means the same amount here. All this money means the same amount here, right? I do the calculation. The calculation give me $20,000. Give me $20,000. This means that if the rate of return or the interest rate is 0, it's $2,000. Sorry, $20,000. Now, if what we are trying to do is we set the interest rate to 10%, 0.1, we do the same calculation, we find out that the present value equals to 8,000 something, right? This is our present value. This is still above 0, right? Remember, our goal is to bring it to 0. PW have to be equal to 0. So we continue trying. We find out, we set it to 0.15, and then we get $4,000 something. If we set it to 20, which is our MARR, we find out that the present value is 900 something. Getting pretty small now, but still above 0. Then we also find out, okay, 0.25, we use 0.25, and we find out now, finally, this number become negative. Right? Obviously, we can continue going to 30%, and this value will be continue decreasing. But, well, just look at this two value here, right? Based on this two value, we know that, when the interest rate is 20%, it gave me $900. When it's 25%, it's gave me negative $1,800 something. Then based on this figure, right, we know once 20% is somewhere here because the value is still positive. The present worth is still positive, right? So above this axis, then we know it's probably somewhere here. Once it become 25%, it's become negative. So we know it's probably somewhere here because it's negative, below the axis, right? Based on this, if this is 20, this is 25, that means our IRR need to be between these two values. It need to be between these two values, right? Between these two values, thinks our MARR is 20, is right here. And then IRR need to be between 20 and 25, but definitely bigger than 20, then we already have our solution or have our answer, right? Okay, we don't exactly know the MAR, the IRR yet, but since you already told me your MAR is 20%, I'm going to say that, okay, this is a sound proposal because I prime is bigger than MARR. So this is a sound proposal. And this aligns with what we find before, right? This is a good proposal. Obviously, most of the time, people don't stop there. People need to know exactly what that value is. And then, based on this, you can say, okay, it's between 20 and 25. Maybe I'll try 22. When you try 22, you find out, okay, it's actually become negative again. Then I can try 21 and then gradually narrow it down. So it's really hard to use a trial and error method to bring it to the exact number. The exact number is actually 0.21557. Truly, it's really hard to get there. It's really hard to get there. But what you can do is actually try to get a pretty narrow, a small number, and then this value is pretty close to 0. Then you can say, okay, this is roughly the IRR. This is roughly the IRR, right? Let's use a trial and error method. Certainly, you can use Excel like we said before, right? You can use Excel like we said before. To do this, we can use the IRR function. Let's say we already know the cash flow here, right? Let's say this is year, and this is the cash flow. For year, we have 0, we have 1, all the way to year 5, right? All the way to year 5. And for the cash flow, first year is negative 25,000. Next few years, always $5,000. And then in the last year, it's become $13,000, right? So we know the cash flow here. Now, what we want to find is IRR. We can still use this financial and to find the IRR function here. The value, we can select these, right? For the gas, you don't really need to put in. If you don't put in anything, it's assumed the closest one is equal to 0.1. So the estimation will be equal to 0.1. Basically, the gas, the change of gas, the computer basically guess multiple times, but every time the change will be about 0.1. So it's just the way to find the optimal solution. We don't need to worry about that. But when we do the calculation, you can see the result is 0.2157. 0.2157. So the interest rate, the internal rate of return is 21.55% something, right? And that means, okay, it's a good investment. It is bigger than 20. It's a good investment, right? So that's how we calculate the IRR. A few things about the IRR, and they have some problems. First, the IRR method assumes recovered funds, if not consumed each time period, are invested at I% rather than at MARR. What does that mean? That means there's compound interest. There's compound interest there. So this is not simple interest, it's compound interest. And whatever money you recover, you're going to have the compound interest of I prime on top of it, right? Sometimes the computation of IRR may be unmanageable. sometimes the computation of IRR may be unmanageable. We'll show why, but it's not always like this. It's not always like this. So there can be times that you just cannot find IRR, or it takes too much computational power to find an IRR. Multiple IRRs may be calculated for the same problem, but are not. Sometimes you do have, sometimes it's not just simple going down, right? In fact, sometimes it can have something like this. The cash flow is so special that when you have different IRR, it can actually generate multiple this. You can actually generate multiple of IRR. Some make sense, some just doesn't, right? And another thing is, the IRR method must be carefully applied and interpreted in the analysis of two or more alternatives, where only one is to be selected. Where only one is selected, right? That means that when you do have multiple IRRs, it doesn't mean that everyone is correct, right? Need to be carefully interpreted to select the right one. There can't be, like I said, they are mutually exclusive, so there can't be two correct IRR. This is mathematically, yes, you can have multiple IRR, but for engineering economy, you can't. You have to carefully select the right one. And that's, a lot of times it's something like this, right? So when you do the calculation, you find out this is -5. This is -5%. This is 15%. This is 75%. This is 120%. Mathematically, they're all correct. Don't get me wrong, right? But for in the context of engineering economy, this is not right. The engineering economy, some values are just impossible. -5 impossible, 75 or over 100 that's not possible, right? Really is to make the rational choice. We think IRR maybe the 15% is the right one we calculate. Here's an example to show you how the multiple IRR can happen. Check this out. This is the cash flow, right? We have a lot of information. We have positive revenue, we have negative cost, negative expenditures, and based on all this, let's find out what should be the IRR. What should be the IRR? And I already have the equation listed down here, right? So we are trying to convert everything to the net present value and then make sure that equals to 0. We don't know IRR, that's what we try to find out, right? For year 1, nothing needs to be added or divided. For year 0, 1 million is 1 million. Year 2, 1 million needs to be divided by 1 plus IRR, right? This is year 1. Year 2 is 1.1 million divided by 1 plus IRR square. Year 3, we do this. Year 4, we do this. Year 5, this is negative, but the function is the same. We do all this, and then we say they all equal to 0. They all equal to 0. Now, how do you calculate? Maybe take a wild guess and try to find out what will be the value. I'll give you 2 minutes to try to find the result. So after you do the calculation, maybe you're going to find two very wild values. But see, this is, if based on all the IRR, remember the drawing we did before, and based on all the IRR, I can draw this, right? At a different point with different IRR, IRR. With different interest rate, I can find out the net present value. And you see, because the curve is something like this, it's keep increasing, and then start decreasing, you actually find out that there are 2 times this curve crossed zero. One is at about 5%, and the other is at about 90%. Well, sorry, 82%, something like that. So based on all this actually have multiple IRR. Now you need to make a decision. Which one is it? It's hard to just based on this to make a rational decision. Okay, 5 is the correct one. Usually we expect to get a lot smaller. We don't expect we can get 80% of revenue or of profit. Right? The interest rate can be as high as 80%, meaning that if we invest something, we can expect yearly 80% of the growth of our money. Usually we don't expect that. But, well, sometimes it can, right? Sometimes it can. Sometimes it is possible for that the interest rate is more than 80%. So really based on based on the cash flow, based on the context, you need to decide which one is the right value, right? So that's the challenge of calculating IRR in many cases. Okay, now we basically have all the information we need to comparing multiple alternatives, and that's going to be our next topic. To compare multiple alternatives, most projects may be accomplished by more than one feasible design alternative. When Northeastern want to build the ISAC building, first thing they did was go out and ask a few qualified designers, architects to provide a preliminary design. Then based on this, they select the best one. But just saying that there's usually not just one way to build a building that can satisfy your needs, right? There can be alternatives. Most of the time also, these are mutually exclusive alternatives, meaning that if we choose one, we cannot choose the other. If Northeastern decide to choose ISAC, then he cannot, that current design, they cannot choose another one. Financially, probably not feasible. Also, well, on that land, only one building can be built. No way you can build two. Right? So they are mutually exclusive. Sometimes, what make alternatives so complicated is that sometimes alternatives may require the investment of different amounts of capital and have different cash flows. Maybe if Northeastern wants to build ISAC, it needs like, I'm just making up money, maybe $30 million, right? However, if they plan to make ISAC 2 second phase, maybe that's $15 million. Or if they choose another design, which don't look that fancy, just a big square box, maybe that could be $10 million, right? So the investments are different, but obviously the return will be different in this case, right? Sometimes it can have different cash flow, meaning that amount could be different, right? But also sometimes the number of years, the period could be different. If we want to build a very, very complex building, it may satisfy all the functions, but need 5 years to finish. We just want to build a very functional one. It only takes 3 years to finish. Then how do you compare 5 years to 3 years, right? A lot of times, if feasible, the do nothing alternative should be included. Meaning that if Northeastern want to decide which alternative is the best from all the qualified companies, qualified architects, one alternative they want to consider is that, okay, if I don't do this, if I don't spend the money, just based on all the infrastructure I already have, what kind of solutions can I come up? How much that will cost me? And to compare all these alternatives and then make the best decision, right? All the things we talked about before can be used to compare multiple alternatives. Um, Obviously, they are used for the mutually exclusive alternatives. They are present worth, annual worth, future worth, internal rate of return, sometimes also external rate of return, which is not part of the content in this class, but that can be used as well. Right? When we do comparing all this, right, the planning horizon need to be considered. Basically, this is a selected time period over which the mutually exclusive alternatives are compared. This is basically a study period. This study period. Right? This planning horizon can be influenced by factors including service period required, useful life of the shorter-lived alternatives, useful life of longer-lived alternatives, company policies, all those kind of information, all those kind of factors can influence, how long we want to design, what kind of a planning horizon do we have. It is key that the study period be appropriate for the decision situation. If you are building a $50 million project, you want to have a good amount of time to do the investment, right? Look at all the alternatives, study them carefully, make sure you have a best option. If you are going to decide what you're going to have for lunch, don't take it too serious. Don't take 2 hours to ponder on what I should have for lunch, right? For our green line expansion, right? Think about how long that take to do the planning. What's the planning horizon for that one, right? I think it's too much. There's another also very important concept which is called useful life. The definition is like this: the useful life of an asset, the time period during which it is kept in productive use. It is kept in productive use. This can be the building that can continue house students for classes, for experiments, for research, for social activities, all that kind of things, right? Like for ISAC, right? This can be also like the Tesla factory newly opened. How long that's going to continue be operating and produce Tesla vehicles, right? Again, in this case, in this situation, the cash flow could be different. Either situation is case one, right? The useful lives are the same for all alternatives and equal to the study period. It's always the same. However, case two could be useful lives are different among the alternatives, and at least one of them does not match the study period. Different, right? So if useful lives are equal, then we can easily apply all the evaluation methods. All this, right? If they are all the same, all the investments going to be 5 years, and here's the cash flow. Okay, no problem. Apply all this directly. However, usually it's not that easy, right? Like we talked before. In case that the useful lives are not equal, then we need to make some assumptions. We need to make some assumptions so that we can actually we can actually do our calculation here. We can actually compare all these alternatives. Be, we need to make some assumptions before we can actually do the comparison. For equal useful lives, with equal lives, adjustments to cash flows we are not required, right? With equal lives, the adjustments to the cash flows are not required. We don't need to do any adjustment. We can just directly compare all these alternatives based on the equivalent worth, either present worth, future worth, or annuity, just calculated based on I. Calculated based on I equal to MARR, right? The investment with the highest equivalent worth will be selected. Obviously, we want the best one. We want the best present value or future value or annuity, right? Here's one example. A company is planning to install a new plastic molding press. 4 alternatives exist. Evaluate the alternatives at MARR equals to 10% with a 5-year useful life for all machines. Please take a few minutes to calculate this. I'm going to show this. We're going to talk about this case tomorrow when we are during the lifetime. I'm going to also write the solutions in our notes. You can find that in our teams. In fact, this is all I'm going to do for this class, all the content that I would like to discuss for this class. For next class, we're going to talk about how do we do the comparison for projects with n equal useful lives. So talk to you next time. Bye.